Hi everyone, this is Madhav. I saw this interesting meme from this video by a YouTuber named Chris recently. He was showing the plight of all high school students when they get to the electricity unit and have all these weird formulas that kind of look the same but aren't really the same, and no one explains to them, what is actually going on. So I thought, okay, why don't we break it down? Why don't we start by talking about the difference between electric force and electric field? And then in another video, we'll talk about how these two are different from potential energy versus potential. Let's start off by talking about electric force. So here we have the equation that you're given in textbooks. Why does this make sense? Why is it the way that it is? Let's move on over to the right and talk about this hypothetical situation where you have two charges, Q1 and Q2. They're generating some force on each other, that's F, and they're a distance of r away. Now, before we start reasoning about what this force is, how it works, what properties of it are, we need two fundamental assumptions. Just like we have certain assumptions in math, like 1 plus 1 is equal to 2, we have to follow these assumptions in physics so that we can then go on and reason about the force that would be experienced by these two charges. One clarification, yes, opposite charges attract. That also means that like charges, in this case, they would repel. So, with that out of the way, let's talk about some reasoning. What we did, I guess physicists did a long time ago, they took charged objects. It could be two protons as I've drawn here, but it could also be any, large scale charged object. They started measuring the forces that they would observe on one object versus the other. Of course, by Newton's third law, the object that this Q2 exerts on Q1, that's the same as the force that Q1 exerts on Q2, because every action has an equal and opposite reaction. So that's one of the observations they made. Place two charges together, the force between them, it's the same whether you're measuring over here or over here. The next observation they made was that if this charge Q1, let's say it's 1 coulomb, and the force is 1 Newton, when you change the charge to be 2 times larger, when you change it to be 2 coulombs, now the force gets 2 times larger. It changes to be 2 newtons. Same if you make this 3 times larger, force also gets 3 times larger, and so on and so on. What they discovered was the force, it grows bigger as Q1 grows bigger, so therefore the force must be proportional to Q1. Same thing with Q2. Experimentally they observed that if you repeat these increases in charge for Q2, you have the same exact effect on the force. So the force is also proportional to Q2. As this goes up, this also goes up. How about the distance r between the two charges? They did notice that there was a link between the distance r and the force that they observed. However, it wasn't that, you increase the distance, the force goes up. And it wasn't that, okay, let's say you make the distance 2 times larger, then the force goes down by 2 times. So if that were true, okay, you make the force 2 times larger and, well, you make the distance 2 times larger and the force goes down by 2 times, then we would say that the force is inversely proportional to r, meaning that as r goes up, you can see 1 divided by r, that would result in a smaller number, so the force would go down as r goes up. But this is not what we found. Instead, what we found was if you make the distance 2 times as large, the force, it doesn't go down by 2 times, it goes down by 4 times. And if you make the distance 3 times as large, the force goes down by 9 times. If you make it 4 times as large, the force goes down by 16 times. So what we found was the force is inversely proportional to the distance squared, not just the distance. Combining all three of these experimental observations together, then the scientists knew that the force, it must be proportional to Q1, Q2 divided by r squared. Just sum those all up in one equation. And if you recall what proportionality means, if I say that, y is proportional to x, what that tells me is that y is equal to mx, where m can be any constant, it can be any real number. Same thing here. So when we say f is proportional to q1, q2 over r squared, we know that there must be some constant. Let's call that constant k, because why not? There must be some constant k such that we can just multiply it, just like we multiplied this x over here. We're just multiplying k over here, and we get Coulomb's law, the equation that we're familiar with. So the key takeaway here is that this equation, the reason it is the way it is just telling us that the force, it grows when either of the charges grow, and it goes down by the square of the distance. So how does this now compare to electric field? Why does this equation look so similar to this? Well, here, when we talked about force, I told you everything was experimental. We were just measuring, experimenting, changing variables, and we noticed these relations. The electric field, it's not an experimental thing, it's a mathematical tool. So the electric field is something that we would compute with equations after we've measured experimentally the force that some amount of charge would experience. So after we've measured the force, we've measured the amount of charge experimentally, then we'd mathematically calculate the electric field. What kind of a math tool is it? Why is it useful? Well, the electric field, it tells us the strength of the electric force in some point, some location, independent of, the charge that the force is being measured with. To explain that to you, I'm going to draw a little diagram. So let's say you have 10 coulombs of charge in this particle. It's not a particle, big sphere, that's a lot of charge, and 1 coulomb of charge. So you have two charges, and this one, it experiences a force of, let's say, 200 newtons in that direction, and this one, it experiences a force of let's say 1 newton in that direction. So if I wanted to compare, what is the strength of electric force over here versus over here, well, we already saw via the equation for electric force, I can't really compare these two directly, because the electric force, it will change based on, the charge values that you put into the equation. So it's hard for us to compare the 200 to the 1. How do we do it? That's why we need a math tool that can let us compare the strength of an electric force in this region over here versus that region over there, independent of these differences in charge. Now, one thing that you might already be thinking, like, just, look at the ratio. This is like 200 newtons for 10 coulombs. That's like 200 divided by 10, that's like 20 newtons per coulomb. And over here you just have 1 newton for 1 coulomb. Like, this is just, it seems to be smaller intuitively. And that's exactly what physicists think too. They're also thinking in that terms of ratio, in terms of division. That's how electric field is defined. The electric field, it's equal to the force that we measure in some region divided by the charge of, the charge of the particle that we're making the measurement with. So if you think about the units here, forces, they're in units of newtons, charges, they're in units of coulombs, so you have units of newtons per coulomb. And as I verbally told you earlier, if you take 200 newtons divided by 10 coulombs, the electric field here is equal to 20 newtons per coulomb, and over here 1 divided by 1, it's equal to 1 newton per coulomb. Now these things are in the same units. Now there's no difference between them in terms of, this charge is different from that, so we can clearly see that the strength of electric force, it's larger over here compared to over here, independent of the charge, because you can think of it as 20 newtons per 1 coulomb, or 1 newtons per 1 coulomb. So that's kind of why we, create the tool of electric field. If we just expand this equation a bit, well, we can just substitute in, our equation, the Coulomb's law that we showed earlier. So instead of writing F, I'm just going to write K Q1 Q2 over R squared over R squared. We're also dividing that by Q. What is Q? Well, Q, it's going to be the charge that we're measuring force at. If you recall from my earlier drawing, as I said, it doesn't matter which charge we measure force at. So one of these I could just label as Q. Let's say I did it for Q2. I could just say, okay, now I've decided this is just going to be written as Q. That's fine. So that's the reason why we have different subscripts. They're just notational differences. There's no theory there. So I could just say, okay, I picked, Q2. That's what I'm going to refer to as Q. And we can then cancel these things out. And we're left with, again, you see a Q1. I'm just going to replace it with a Q, just a notational difference, because now we're like, okay, so discharge 10 coulombs, it's going to be divided out, and we know that there must be some other charge that has the electric force, there must be some reason for it. So let's say you have like negative whatever coulombs, negative Q coulombs over here, and that's why there's a force from the positive charge to the negative one. So you're just left with, that Q. KQ over R squared. I just took away the 1 because it's just a notational difference. Like there's some charge over here, you divide by the other charge. So that's how electric field, that formula came to look so similar to electric force. It's just a mathematical tool that we got once we calculated the electric field. It's equal to the force per unit of charge, and the tool is useful because it lets us calculate or predict, what is the strength of the electric force in a region independent of what charge we're actually measuring with.